everybody, thank you for joining me once again today, where hopefully today we can finally put this calories in, calories out, calorie counting discussion around energy and nutrition to bed for once and for all, because I'm really tired of this topic personally. However, I'll do my best to present the information to you in such a way that hopefully, if you haven't got it yet, you finally click onto it today. It's fine that you haven't got it yet if you haven't. There are a couple of things going on here. First of all, everyone has been told their whole lives that a certain thing is true, and it's never really been questioned seriously. And as such, it's just accepted as a truth, and anyone who says otherwise is some kind of heretic and needs to be not taken seriously. So that's part of it. And the other thing that's going on here is that there's a little bit of nuance here that people need to actually stop and think about. And that is my job today, is to give you that nuance around this idea of calories in our food, calorie counting in nutrition, and its utility or otherwise for attempting to make changes to our body composition in some way. So let's crack on. Bear with me while I get the basics out of the way, and then we'll kind of, in a relatively discursive, hopefully discussional way, I will hopefully get this message across to you today. So, buckle up. Here it comes. Right, let's start with a discussion on energy, because we're told that the intake of our food is all about energy. Its effect on our body composition, our body mass, our weight is all about energy. The so-called energy contained in our foods is described as a calorie or a number of calories. So let's go through these basic first principles and get it clear in our heads what it is we're talking about so that we are all on the same page. Okay? So, what is energy? We need to understand that energy is a construct. What is a construct? A construct is an idea. It's a model. It's something that we have put together as an intellectual tool to attempt to help people to comprehend a concept or an idea, or to give it some place in or context in reality. And I'll give reality that one. The problem is, just because a construct exists and is used commonly in everyday parlance, that doesn't make that concept correct, valid, robust, or of utility scientifically or in practice. The idea that we have about energy is that it's some kind of thing. It's not a thing. Things are mass, matter, stuff that has a weight under gravity, stuff that can be acted upon by forces, which we'll get to soon, stuff that has an objective reality as close as we can get to anything having an objective reality whatsoever. That's also for another day. The only time energy is actually a thing is when energy is itself found, observed by us to be in the form of mass. Things. Mass is a condensed form of energy. Mass and energy are interchangeable mathematically via the classic equation E is equal to mc squared. That's kind of above the scope of this discussion, though, so we don't really need to go there so much today. We just need to understand that mass can be converted to energy, and that mass is itself a condensed form of energy in the first place. Okay. All of that being said and out of the way, mass is thought of as the impetus or the motive force for doing work. Work, in turn, is defined as a given force applied over a given distance. And in turn, force is defined as a certain mass accelerated by a certain amount, thus bringing in the meter of time, the clock, if you like. Now that leads us to some serious problems in terms of operationally, scientifically defining what energy is. And here's what those problems are. Both mass itself and also acceleration are relative to inertial frames, as is time. All of those things are relative according to inertial frame. Okay? So there is no externally valid, checkable definition available for work, force, mass, acceleration, distance, or time. They're all fluid. They're all part of a four-dimensional fabric called space-time after Einstein, basically. So we've got some problems, haven't we? All right? You cannot measure energy itself. There is no meter that will measure energy. The only thing that can actually be measured objectively using some bit of kit is the so-called work that is being exerted on some matter somewhere in some way, or indeed the existence of mass itself, which can be weighed under the force of gravity, thus telling us how much of it is there and thus giving us an idea of how much condensed energy is there in that form. Neither of those is measuring the energy itself, only its effect on mass, either by creating it in the first place, or indeed by acting upon mass already created and condensed into that form and causing it to change its momentum by way of applying a certain acceleration to that mass, i.e. a force, that force being applied over a certain distance, which is objective, giving us the measurement of work. That's the thing we're measuring, not the actual energy. I hope that's as clear as mud. All right, so the whole idea of energy is circular. It's internally consistent mathematically, fine, but there is no external validity or reality to it. I hope that's gone up some flagpoles. So what is energy? An idea, a construct. Work is the tangible thing that can be measured. Okay, fine. Let's move on from there, shall we? There's an idea floating around called the conservation of energy. Remember that energy is a construct. What the conservation of energy suggests is that the measurement of the amount of energy, by virtue of measuring its effects on matter, using some bit of kit, that is always conserved. The amount of total energy in a system of interacting bodies remains the same. Energy can be transmuted between different bodies and changed from one form to another form, which is detectable by its effects differentially on matter in different ways. Fine. Okay. The conservation of energy was claimed probably prior to Emily Noether, but actually formalized by Emily Noether when she proposed mathematically the relationships between deep symmetries, mathematical alterations, I guess, adjustments of various different equations describing the physical behavior of matter, excuse me, and energy, gave her the mathematical internal consistency, the proof, if you like, to suggest that energy is always conserved in an interaction between things. Okay. Emily was actually wrong. Energy is not conserved at all times, universally across the universe, at all places and all times. Okay? Why do I say that? Well, go and look up Doppler redshift of photons when they translocate across the universe. There is an example of the so-called law of conservation of energy breaking down across interstellar distances and being thus false. Okay? That said, disregard all of that really. It's just for your interest, because to all intents and purposes, Emily Noether was and is correct regarding energy and its conservation in the context of our everyday lives, given our shared inertial frame of reference and our agreement between the measurement of distance, time, mass, etc., being that we share that same inertial frame of reference with one another to all intents and purposes. Okay, so that's cool. Let's just say conservation of energy is a true thing in practice in our lives. Fine, no problem. So the translation of the whole mathematical triatsy, if you like, can really be boiled down to the common, colloquial, everyday language version of the law of conservation of energy, which basically says energy cannot be created, nor can it be destroyed. It can only be changed in form from one to another. Kinetic energy to potential energy to kinetic energy to potential chemical energy, radioactive energy, electromagnetic radiation, according to the electroweak forces, ionizing radiation as per the strong nuclear force, etc. Fine. Okay. Energy comes in different forms and it can be changed from form to form, but you can't make energy from nowhere and it doesn't disappear anywhere either. It just is. And I'll give is that as well because we've just discussed that energy is not. It's a construct. It's an idea. The thing that is the matter upon which the energy is acting, thus inferring that energy is, but we still don't know what energy is other than some circular, internally consistent argument as to what it might be. I hope this is going up some flagpoles. What I'm suggesting to you is the surety with which people talk about energy, conservation of energy, calories, nutrition, and thermodynamics is utter nonsense. This water is so muddy, you can't see the bottom. You can't see below the first inch, let alone to the bottom. Okay? And I hope that what I'm doing here, by speaking these scientific truths to you, is rattling your cage, shaking up your confidence, and making you think, hang on, we really haven't got this together at all, have we? Because that is the correct view on this issue. Well, you'll have it together by the end of the discussion, because not only am I here to pull things to bits, I'm here to put it back together for you in a way that does make sense, and that is both internally and externally valid, and that all observers can agree upon once they drop their egos and their preconceptions and their false ideas and replace them with correct ones. So let's do that. There's another idea floating around called conservation of mass. Mass being a form of energy, energy is conserved, therefore mass would be the logic, or the pseudo-logic, the apparent underpinning logic. However, the conservation of mass is absolutely, definitely also false. Completely false, much more false than the conservation of energy. Even in our everyday lives, the conservation of mass is demonstrably absolutely false. And I'll give a couple of examples of that in just a minute. All right. Anyway, the so-called law of conservation of mass, derived from the one for energy, would therefore take the form of mass can neither be created nor destroyed. Well, that's obviously false, isn't it? Because, well, here's the problem. If mass cannot be created, then it cannot exist. Because for something to exist, it must be created. Mass does exist objectively. We can measure it. We can use kit to weigh it under the force of gravity, the pseudo-force of gravity, the space-time curvature, which we understand as and interpret as gravity. Fine. It's a real thing is mass. It does exist, therefore it was created at some point from something, apparently energy, which we still don't know what that is. Okay. So there's the problem with the conservation of mass straight away. It cannot be created. Well, yes, it can, because it exists. All right? The other example of mass being created is this. At CERN, they basically accelerate particles to 99.999 something percent of the speed of light and crash them into each other. And what happens is you can take X amount of mass in the form of a couple of protons, smash those together, and out of that sprays a whole bunch of other particles, which sometimes weigh many, many orders of magnitude more than the amount of mass that was put into that interaction in the first place. In other words, so much energy is going into that kinetic crash of those two protons together that much of that energy is being condensed into the creation of matter that was not there previously. So mass can be created, and we have done it using particle accelerators. So that's definite. All right. So mass cannot be created or destroyed. False. Now, also the other side of that, mass can't be destroyed, would say the conservation of mass. Well, yes, it can. Ask anyone that was alive, or that is alive, that was alive also, and was in the vicinity of Hiroshima, Japan, on the morning of the 6th of August, 1945, whether or not mass is conserved, and they will quite clearly tell you that it is not. Okay, so we're done with that one. Conservation of mass, definitely, absolutely, even to all intents and purposes in our everyday life, false. So forget that one. Right. Now, of course, the people that say, well, the way to lose weight, by which they mean fat, and should say that, because mass is made up in a lot of different ways, isn't it? Skeletal mass, muscle mass, fat mass, mass of water in your body, connective tissue mass, etc. Okay? So when you're talking lose weight, you really ought to say lose fat if that's what the goal is, specifically. That's just a little bit of science for you. Sorry about that. Anyway, the folks that say the way to lose fat is to control your calorie intake. We'll get to calories in a minute. And that this is underpinned by the law of thermodynamics. And what is anyone talking about that says otherwise? Don't they understand science? This is absolutely a universal law of the universe, they say. Usually I say to such people, great, would you like to quote for me the first law of thermodynamics? Invariably, they'll say one of, well, energy can neither be created nor destroyed, only changed in form, which is not the first law of thermodynamics. That's the law of conservation of energy, which we've covered already. So you don't lecture me on thermodynamics if you don't know what the law of thermodynamics says, the first law. Or they're even less educated than that, like, for example, Dr. Norton, who will say that the first law of thermodynamics suggests that mass can't be created nor destroyed, only changed in form, which is definitely false because we know that mass is not conserved. And, well, have a look at the first law of thermodynamics. It's on the screen for you now. It says delta U is equal to Q minus W. Period. That's all it says. Nothing else. That is the first law of thermodynamics. Delta U equals Q minus W. So let's translate that into English, because math is a language all of its own. Delta U denotes the change in the internal energy, which is an intensive property, of a closed, in capital letters, closed thermodynamic system. And a closed thermodynamic system is one in which heat, energy, and physical kinetic work can be exchanged across the boundary of that system. Ergo, that system can gain or lose internal energy in those two forms. However, matter cannot be exchanged either in or out. That is what the first law of thermodynamics says. It is a case-limited example of the so-called law of conservation of energy. Okay? So the internal energy of a system, a closed thermodynamic system, is always equal to the specific heat energy supplied to that system minus any work done by that system on its surroundings, the exchange of that energy in some way to some other body. Okay? That's all. What I would like you to do now is pause this video and look very carefully through that equation, the first law of thermodynamics. The internal energy of a closed thermodynamic system is equal to the specific heat capacity, if you like, or the heat energy contained in that system or supplied to it, minus any work expended by that system, thus allowing energy to escape to its surroundings. Now, pause the video and think very carefully for as long as it takes. Please point me, if you'd be so kind, to what part of that equation refers in any way to physical matter, mass, in any way. I'll wait until you get back. Okay, I'm going to assume you're back because you've hit the pause button. So you've worked it out. The answer is the first law of thermodynamics, specifically in its formulation and formalization, specifically, explicitly excludes any discussion whatever of mass. Doesn't it? So is the first law of thermodynamics applicable to the mass of your body? No, it isn't. Is it applicable to the mass of any component of your total overall mass? No, it isn't. Is the first law of thermodynamics then an appropriate law to refer to when discussing body composition or body mass in any way, shape, or form? No, it isn't. Pretty much I could end the lecture there. We're done. But I won't. I'll just labour the point to make it absolutely clear to everybody, hopefully. Here we go. Heat energy, Q, in the sum that we've just looked at. What is heat energy? Heat energy is a form of kinetic activity, kinetic energy, movement. It's the movement of atoms which are encompassed by a body, a system. Okay? What kind of movement is it? It's vibration of molecules that are able to, like a triatomic molecule is able to vibrate. Water is an example. It will vibrate around its central atom. The oxygen molecule, the two hydrogens will do that. The faster they do that, the hotter the water is. Okay? How else can they be affected? Well, a single atomic atom or a molecule can rotate in a number of different ways, X, Y, and Z, really, can't it? It can rotate around its center of mass. The faster it rotates, the hotter it is. Okay? Or that molecule of water or that atom, as the case may be, can, so long as it's not held in place by its interaction with the other molecules around it, such as in a solid structure, it can move. The faster it moves from A to B, the hotter it is. Okay? So how do we translate or transmit that movement energy between the molecules in one body to the molecules in another body? Given that electrons are the outer valence interactive parts of any atom, ergo any molecule to speak of, it is the electrons that will interact between one atom or molecule and another. How do electrons interact with other electrons? By repelling one another using the electromagnetic force, which is translated between one electron and another that are repelling each other because they're both negatively electrochemically charged. That force is transmitted between those electrons using a photon. That is the force carrying particle, the field, if you like. All right? So the way to translate heat energy from one body to another is to shoot a photon between those two things. The loss of the photon in the thing that was moving fast slows it down. That's the energy quanta that's been exchanged. The thing that's gaining the energy is absorbing the photon that's been shot at it. It speeds up, gets hotter. Okay? So heat flows from a hot place to a cold place, always in that direction, pretty much, because of, well, entropy, which is for another day. That's what the second law of thermodynamics is about. Today we're dealing with the first law, so let's stay with that. All right. So how much matter, how much mass has been exchanged between one thing and another thing by translating heat from one thing to another thing? Well, the rest mass of any given photon, and all photons being identical, is none. It has no mass. It does not weigh anything. It does not interact with the Higgs field, is another way of saying that. Its mass is none. So, any amount of mass, matter, anywhere in the universe, pretty much, plus or minus additional added mass or loss of mass equaling 0 photons, leaves the original mass unchanged in its inertial frame of reference. It's the same. It hasn't. You can't increase something by adding 0 to it. Neither can you reduce something by removing 0 from it. So no amount of absorbing photons nor emitting photons will change your weight, your mass. It's impossible. That is against the laws of physics. Okay? So hopefully now you've got it. I mean, this should have been redundant, but perhaps it wasn't. Maybe that's the thing that clicks it off in your mind and you go, oh, now I get it. If not, that's fine. We'll just carry on to make it even clearer, hopefully. Hopefully. How do you change your body mass? Or indeed any component of your body mass? Well, the only possible way to change your body mass is to absorb mass or to excrete mass across the system boundary. The very thing disallowed by the very formalization and formulation of the first law of thermodynamics. Okay? Humans are not closed thermodynamic systems. We can absorb mass into our bodies from the external component, from outside of the system, and we are also able to, and in fact do, exude mass from the body to entropy, to the universe outside of the system boundary. Body mass and body composition changes are both mass in, mass out activities, not energy in or energy out. The so-called calories contained in food, the so-called energy contained in food, is actually used to take an ADP and a PI, an inorganic phosphate, and chemically force those things together against their Gibbs free energy desire to be separate things, force them together. It's the activation energy required for that chemical interaction, and we get an ATP out of that. So ADP plus PI has a mass which is the mass of the ADP plus the mass of the PI. Jam those things together chemically and make an ATP. The mass of that is unchanged. No mass has been gained at all. Okay? What do we lose? Well, the carbohydrate or the fat, or in an emergency situation, the protein, or indeed if there's alcohol available to the system, then alcohol as well, is chemically broken down by interacting it, to all intents and purposes, in the most parsimonious way with oxygen, which you get in from the atmosphere by breathing it into your lungs. That interaction of oxygen with those food masses, those substances, that stuff, the chemical results of that are carbon dioxide gas, which has a mass, it has a weight, it can be weighed and measured, and you expel that at the lungs. The other chemical result is water, H2O, which will be added to your pools of body water, and then basically your kidneys and other organs work in concert to control the level of water in your body. Either it's retained or it's excreted above a certain level, and when you excrete that water, that's a loss of mass in your urine. That's it, pretty much. How else can you lose mass? Well, you can dehydrate yourself, such that your water balance drops below where your body homeostatic mechanisms would normally want it to be. You're way less then. The exact amount of energy lost in so doing is none, because how much energy is there in water? None at all. Oops, calories are starting to look a bit shaky, aren't they? All right. How else might you lose mass? You might have a surgical procedure which results in the loss of some matter, some physical stuff from your body. Maybe you have your appendix out. After the operation, you will weigh, all things else being equal, exactly the weight of your appendix less. How much energy did you lose? Well, you could say the matter that was the appendix has been lost, and that matter is a condensed form of energy, in which case it's millions and millions and millions of calories because of the E equals mc squared sum. Or you could just say, well, to all intents and purposes in everyday life in terms of in the human body, we're not atomic bombs, so mass remains mass. So the actual energy, how many calories of energy were lost there? None, in effect. So whoops, there's another example of where it breaks down. The only way to gain mass is to retain foodstuffs in the form of, well, proteins, carbohydrates, and fats. The only time you do that is when you consume more mass than your body chemically interacts with the oxygen from the environment and then expels. Nothing whatever to do with energy. It is the need for Gibbs free energy to produce ATP that stimulates the body to undergo that chemical reaction, sure. But that's not the energy transfer, is not the thing that causes the change in mass or the change in body composition. It's the balance of the use of mass, the loss of mass versus the intake of mass. So what we're saying is body composition and body weight are both absolutely, unequivocally, undeniably, and unassailably mass in and mass out, not energy in and energy out. And there are many examples of how you can gain or lose mass independent of energy intake. Even if you were able to accurately gauge calories in effect, or calories out, in effect, in the real world, in your body on any given day. You can't do that. And I've made several videos previously explaining why it is that there is no way, scientifically, practically, that you can possibly measure how many calories you are consuming, nor how many you are losing. It cannot be done. Even if you could do it, though, there are examples of the loss or gaining of body mass and or changes in body composition that have nothing whatever to do with energy. Here is just one example. Between the 1st and the 14th of January 2023, I lost 15 pounds in weight on a scale. Prior to that, for many years, I had been consuming a diet which was nominally very close to, if you believe you can get very close by writing down what you've eaten, you can't, but let's say you could, roughly 1,800 so-called calories of intake of energy per day was my normal, habitual intake of so-called energy. Between the 1st and 14th of January 2023, I lost 15 pounds. During that time, I also consumed 6,000 to 6,500 calories per day, every single day, 14 days in a row. How does that work? It simply doesn't, if calories in, calories out were remotely correct. It isn't, and I've given you the reasons why it isn't in this discussion. Hopefully they've gone up your flagpole. Hopefully you have understood fully and finally. If not, please do feel free to comment under this video, ask questions, and I will try my very best to clarify as parsimoniously as I possibly can. But I think that is and should be as clear as it's possible to get. I hope that you have understood all of that. Here is some interesting reading which backs up what I've been saying. These are published peer-reviewed articles that explain how body mass and body composition are absolutely mass in and mass out, and not energy in and energy out in any form, including calories. Do feel free to look these up and read them for yourselves and attempt to understand. They're quite technical, obviously, being scientifically peer-reviewed mathematical treatments mostly, but feel free anyway to dive in and see what you can get from those. In the meantime, if you want to follow me on all the various social medias and see what I'm up to and keep tabs on me, because I'm a dangerous lunatic or something, then perhaps you could follow me on the YouTubes here, or perhaps you might follow me on the Instagrams. You can follow the fun and games I have with other folks on Twitter, just for a laugh, where you can actually speak freely, or at least relatively. And indeed, there is a Facebook page that you can subscribe to there as well on the screen for your joining up and subscribing pleasure. All right. Also, underneath every one of my videos on YouTube, you will find a list of links to about 5 or 6 other YouTube channels that I also maintain, run, and create material for that you may like to subscribe to. That'd be great. I'd appreciate that. Thanks very much. And also, you will find links to how you can get hold of me if you want to consult with me professionally or whatever, that sort of thing. And or you might want to buy some merchandise from my fine merchandise store. And or you might want to investigate the stem cell nutrition products with which I have joint ventured in the last several years to great effect. In the meantime, much respect. Hope you got something out of this today. I hope that finally puts it to bed for you. I hope that we now all understand calories in, calories out is dead in the water. It's done. It's finished. There is nothing to debate any further. Anyone that wants to debate it with you, I suggest what you do is you link them to this video and ask them to watch it from start to finish. It's only less than 40 minutes long. I think it covers it off. I really do. And if you don't, then perhaps, ask me some questions under the video. Awesome. See you next time. Probably when someone will be wrong on interwebs, because that doesn't look like slowing down anytime soon, does it? See you then.